As you can see, I'm on board ship. But where am I? This is something I can't immediately find out. And in olden days, a sailor who didn't know where he was liable to find himself in deep trouble. So he had to be a good navigator, and all navigation is based upon astronomy. Even maps are based upon astronomical principles, and the first man to do that, and to draw a world map which was based on anything more than faith and a good deal of hope, was Ptolemy of Alexandria, and he did this in the 2nd century AD. He was a pretty good astronomer cum geographer, and on his map you can see quite a number of recognizable features, despite the back-to-front position of Scotland. The sailors of pre-steam days used maps, of course. They had to. But when you're out of sight of land, as we are now, and have been for some days, how do you find your way? There's an awful lot of sea, and you can't read your way by means of definite marks, because there aren't any. In fact, you can't read your position from the sea or the land, so there's only one way to do it, by using the sun and the stars. You've always got the sky. There are two things you've got to know. Your latitude, which is your distance north or south of the equator, and your longitude, which is the east to west measurement. And this is done by using an instrument called a sextant. And using our sextant at the moment, no less a person than Commander Hatfield, whom all viewers of the sky at night will know. Henry, what exactly are you doing?
I'm measuring, Patrick, the altitude of the sun at local noon. The altitude of the sun, of course, is the angle between the horizon, which is over there, and the sun is up there, very bright. If on this sextant you set the angle to naught, there is the angle there reading naught, you notice that that mirror and that mirror are parallel. If I increase the angle on the sextant, watch this mirror move. There, it's moving now. Now, through this telescope, I can look straight through that piece of the mirror because it's not silvered, the left-hand side. The right-hand side of that mirror is silvered. The light from the sun strikes this mirror, goes through that shade to protect my eye, and you'll notice it's in front of the telescope, hits the silvered part of that mirror, comes into the telescope. When you look through the telescope, you sit the sun on the horizon. Now, I'll sit it on the horizon now. There it is. And it is on the horizon now. And the angle of the sun above the horizon now is 54 degrees and 58.5 minutes.
Well, that gives you the height of the sun above the horizon. But how do you find your latitude from that?
Come and look, and I'll show you. This diagram represents the Earth. That's the center of the Earth. There's the North Pole. There's the South Pole. Here's the equator. This circle is actually our meridian. We are here. The angle that I've just measured is this one. The altitude, as you remember, of the sun, that angle between our horizon and the sun. The angle that I want is not the altitude, but this one. This angle is the zenith distance, and the zenith is the point right over my head. You'll also notice that it is the point which is the extension of the line which joins the center of the Earth and me. Center of the Earth, observer, zenith. This angle is the one that you always want when you're taking any sort of sextant observation at sea. You'll notice I've shaded it, pale grey. We'll come back to that in a minute. There is the sun from us. Here is the sun from the center of the Earth. These two lines are very, very, very nearly parallel. Not quite. The sun is not quite at infinity, but for navigational purposes we may assume that it is at infinity. Since these two lines are parallel, that grey angle equals that grey angle. You notice they're both called zenith distance. Now let's look at the situation as viewed from the center of the Earth here. Here is our zenith distance, which we have measured. This angle is the declination of the sun. It's the angle of the sun above or below the equator. Here's the equator. There's the declination of the sun, that angle. We can look that angle up in the nautical almanac, which is really just a timetable of the sun, and in actual fact the stars too. Now, We can look this angle up. We've measured that one. What happens if we add them up? We get that angle, and if you look here, that angle is our latitude. If you add up declination and zenith distance, you get latitude straight away. And here we have the little thing to remember: latitude equals zenith distance plus declination.
Well, this is all very well for the sun, but what about using the stars, and the pole star in particular?
Well, you can get your latitude from Polaris pretty easily. You measure the altitude of Polaris, you apply a correction which can be looked up in the Nautical Almanac using your own wristwatch. You apply this correction to the altitude of Polaris, and there is your latitude directly.
So, in fact, you can use Polaris at any time?
No.
When you can see it?
When you can see it and a horizon. And you can only see Polaris when it's dark-ish. You can only see the horizon when it's not too dark. And you can only see both during about 15 or 20 minutes just after sunset and 15 minutes just before sunrise.
Well, you know, many years ago, when I was an Air Force navigator, we used to use astronavigation quite a bit, and we used tar shots with an artificial horizon.
Yes, you may have done, and I suspect that your errors were probably something of the order of plus or minus 10 miles.
True enough.
My sextant, on a good day, will give me an error of perhaps 2 miles. It shouldn't be greater than 3.
So in this way, by using your tables and a sextant, you can get your latitude pretty accurately and very quickly.
Yes, indeed.
Well, let's assume for one moment, then, that you know your latitude. The next thing is longitude, and this is very much trickier, because, for one thing, there's no obvious standard of reference. We measure our latitude from the equator, which is midway between the two poles, but there's no definite line for longitude. And the one that's been selected is the line on the Earth's surface running through both poles and Greenwich Observatory. And this was selected by international agreement in the days when international agreement was a great deal easier to obtain than it is now. And I think, Henry, this is what I hand back to you.
Thank you, Patrick. The problem, as ever, centres around this angle, the zenith distance. That angle doesn't have to be measured in the plane of the meridian. It can be measured in any plane. It is, of course, always measured in the line joining the observer and the sun. Supposing that we do measure that angle, and supposing that we can find out the position on the Earth where the sun is overhead at a particular time, then we can do something with that angle to find out where we are. Now, this position, it's called the subsolar point, is given in the Nautical Almanac, which is a timetable. There is the position at 1700 on the 29th of June today. The longitude of the position where the sun is overhead at 1700 is 74 degrees, 9 minutes west, and the latitude of that position, which is the declination of the sun, is 23 degrees north, 12.8 minutes west. Now, if we plot that position on this globe, you'll find that it's on the western end of the island of Cuba, just there. Supposing that that is the zenith distance, you can see that it is 10, 20, 30, 40, 50, 2 degrees. Put one end of the dividers on the point on the Earth, which is right under the sun. Scribe an arc over here. We are somewhere on that arc there. When we took our latitude sight, we found that we were in 23 degrees north. That is 23 degrees north. Therefore, we are there.
Just about where we are at the moment, in
Yes,
fact.
indeed.
But of course, Henry, all this depends upon knowing GMT, Greenwich Mean Time, and we're an awfully long way from Greenwich, and that presumably is where your really accurate timekeeper comes in.
Yes, and here he is. This is a chronometer, a very carefully made clock. The main difference between this clock and clocks which you have ashore are these gimbals. You can see it'll swing that way and that way. These gimbals, of course, are to keep it horizontal when the ship is rolling. There's not much movement on the ship now, as you can see, but if there were, that clock would remain stable.